The topic of this lesson is improper integrals. And so what those are, let me explain a little bit geometrically. So far in the course we've looked at areas of bounded regions, and we've used integration to find those areas. Now we're going to go a little bit further and we're going to look at areas of some kinds of unbounded regions. And the areas, the integrals that represent the areas of these unbounded regions are going to be called improper integrals. And we're going to split these unbounded regions into two types. And the first is commonly called type 1, and that is when the region is unbounded on the left or on the right. So an example here, right, this region that we're looking at between our function graph and the x-axis up until this point A, but with no bound on the left, no bound. And so the way that we would write this, the integral that represents the area of this region as the integral from minus infinity to this point A of f of x dx, right? From all the way out, right? From somewhere that you cannot even start, minus infinity to point A. The same thing on the other side. If we were going to the right, so a region which goes on forever from a point A to infinity, bounded by the x-axis and the function graph, we would write this integral, the integral that represents the area of this region, as the integral from A to infinity of f of x dx. Those are improper integrals of type 1. Type 1. Type 2. Type 2 improper integrals are going to be when the region is unbounded above or below. Above or below. So here is one where the region is unbounded above. The area just keeps on going, or the region just keeps on going. And here, well, this is between A and B, and so we would write something that looks perfectly normal. Something that looks perfectly normal. The only issue here is that x equals b is a vertical asymptote. So that function just keeps on climbing, and so does the area. Below, well, same kind of deal here. I've got a region which continues going on unbounded below. It also is from, seemingly innocently, from A to B. From A to B. The only deal is that this time A is a vertical asymptote and everything is below the axes. And so we would write the integral from A to B of f of x dx. And might not notice that this one was in fact improper. And that is my first comment to you here, is that it is easier to recognize a type 1 improper integral than a type 2. How come? Because you can see the infinities right there and right there. The infinities are in the bounds. Whereas in type 2, it looks like a normal integral if you're not paying close attention. So how do you tell? How do you tell for type 2? You need to know the function. You need to know something about f of x to know whether that region is unbounded above or below. So both of these represent types of improper integrals. We're going to focus on type 1 for the moment, and we will go on to type 2 in another video. So let's be a little formal with the definition of these from our textbook. So the definition of an improper integral of type 1. So let's read this carefully. If the integral from a to t, where t is just some number bigger than a, if this exists for every number bigger than a, then this improper integral, which is the integral from a to infinity, which we had before, is given as a limit. It's given as the limit, as t goes to infinity, of the integral from a to t of f of x dx. And this is worth taking a second and unpacking a little bit more. This is actually giving us a procedure. If we were to look just at this part here, the integral from a to t of f of x dx. That is just going to be a simple anti-differentiation and FTC2. So if we had just this part, then we would not have any issue. We would know that we're looking for an antiderivative f of big F, and we would do big F of t minus big F of a, and we would be done. So what an improper integral does is it comes and adds a second step to that. It adds a second step, which is a limit. And so once we have the answer from the first step, we are just going to do the limit as t goes to infinity of that answer. So the definition actually gives us a procedure, a two-step procedure to evaluate this, which we are going to do momentarily. Step 1, basic integration with the FTC, part 2. Step 2, a limit. So all of your limit calculations from Calculus 1 are going to be put to good use here. So that was where the region was bounded above, where we had the infinity above. We have a similar definition. If the region is bounded below. No, I said above and below. Left and right. The infinity is above, but the region is on the right and on the left. So if the integral from t to b of f of x dx exists for every number t, this is less than b because we are looking on the left this time. Then the integral from minus infinity to b of f of x dx is defined in an exactly analogous way. So the limit as t goes to minus infinity of t to b of f of x dx, which again gives us a two-step process. Step 1, calculate the antiderivative and use FTC2. Step 2, take the limit exactly like we described for part A. There is a little vocabulary here to know. If these limits exist, right, if this one and this one exist, these integrals are called convergent. They are called convergent if the limit exists, and they are called divergent if that limit, either of those limits, doesn't exist. There is a third case. There is a third case to consider, and that is what if we want to look at a region which is unbounded both sides, So from minus infinity to infinity, in other words, over the entire real line. So what do? Well, we use something which reminds us of a property of integrals. We split the real line at some point A. Any real A can be used if the integrals are convergent. And then we just add them together. But this is an important point to emphasize. This works if both of these pieces are convergent. If one or both are not convergent, right, then this procedure does not work. So this definition works only if the two separate pieces are convergent. Okay, let's go ahead and look at a couple of examples to put these into play. So we are going to determine if the following are convergent or divergent. Those are vocabulary words that we just learned. Whether the limit that comes out of these integrals exists, right? This convergent is the limit exists. Divergent is the limit does not exist. So let's look at the first example here, number 1. So the integral from minus infinity to minus 1 of 1 over x squared dx. Here is our function. Here's the graph of y is equal to 1 over x squared. And so if I'm looking from minus infinity to minus 1, I'm looking at the region here under the graph from Well, from way out there on the left all the way up to minus 1. And so the definition tells me that this integral is a two-step process, right? It is the limit as t goes to minus infinity. So this minus infinity has been replaced by t. The minus 1 stays in place, and then the function is just recopied. So step one here is antiderivative, right? So we have x to the minus 2, antiderivative of x to the minus 2 dx is x to the minus 1 over minus 1 plus c, or minus 1 over x. So there's the antiderivative that we are doing FTC2 on. So evaluate at the top minus the bottom. Evaluate at the top, you get 1. You get minus 1. Minus minus, again, plus 1 over t. So there I have done. This is the application of FTC part 2. That is done. So now we move on to what I had called step 2 above, which is that limit. That limit here. So the limit as t goes to minus infinity of this. Well, the limit of a constant is just 1, and if we write our thought process, this is 1 plus 1 over minus infinity, right? This is a thought process, so I'll put that in quotation marks. 1 over minus infinity, 1 over anything that is growing without bound will tend to 0, so 1 plus 0 gives me 1 as my final answer. So that means, in terms of the definition, that limit exists, and so the integral is convergent. The integral is convergent. And what that is telling us is that this area here is going to tend towards 1 square unit, right? So it is growing and growing and growing as we go out there, right? There's more and more area, but it is growing so slowly in a way that it will tend to 1 square unit. Now, that might seem counterintuitive to you, but you have seen things that grow forever, but not to infinity, right? So a function, functions that grow, they are increasing forever. They are increasing forever, but they don't go to infinity. They have asymptotes. And so what is happening here is sort of an asymptotic increase of area. I'll talk more about that in just a moment. Let's look at the second example. So second example, we've got an integral from 1 to positive infinity. So now we are talking about a region which is on the right of 1 over x dx. So here is our graph. Here is our graph of y is 1 over x, and I'm looking at the region from 1 going on forever on the right, So 1 to positive infinity. Again, using the definition of the improper integral, this is going to be a limit as t goes to infinity of the integral from 1 to t of the function. Step 1 again. Step 1 is the FTC. We're anti-differentiating. So step 1, antiderivative of 1 over x, ln of the absolute value of x. Here we have done FTC part 2, ln of t minus ln of 1. And so next step is the limit then of this expression. We are thinking here ln of infinity minus ln of 1 is actually just 0. Ln of infinity, how do you think about that? You have to know the logarithm graph. As the logarithm, or as x goes to infinity, what happens to the logarithm graph? It also grows very, very slowly. This, again, is a thought process, so let me put that in quotation marks. But ln of infinity means that this limit is going to infinity, or so the limit does not exist. And if the limit does not exist, the integral is called divergent. The integral is called divergent. So this area, the region here, right, actually accumulates and keeps on growing. There is an infinite amount of area as we go off to infinity, whereas up here there was only 1 unit as we approached 1 unit. So why the difference, right? These functions, they look fairly similar. They look fairly similar. And their graphs have similar shapes. They are both rational functions, and yet there is a difference. One gave us a convergent integral, the other gave us a divergent integral. So what is going on? Why the difference between these results? And that difference is, well, I mean, it comes down to the rate at which the area is growing. In the first example, 1 over x squared, in 1 over x squared, the area was going slowly enough that the total area converged to 1. But in the second example, 1 over x, there was enough of a difference in the rate of growth of the area. And what measures area? Antiderivatives. So the technical answer, right, the first was an intuitive answer, the real answer comes about is to the antiderivatives. The antiderivatives, when we have 1 over x squared, the antiderivative is this. That is measuring area growth. And what happens when we take the limit here for this antiderivative as we go? Well, in this case it was minus infinity, but the same thing would be true on the other side. What happens here? That goes to 0. That goes to 0. In the second example, the antiderivative was very different. The antiderivative was not a rational function anymore. In the second example, the antiderivative was a logarithm. And when we apply the limit to a logarithm, you get an infinite answer, right? And so the difference between them has to do with the antiderivatives that come out from the integration, and those antiderivatives, of course, are measuring the area and the change in area. So, one more example. The definition had 3 kinds, right? Left, right, and both left and right. So let's look at that. Example number 3. We're going to evaluate the improper integral from minus infinity to infinity of 1 over x squared dx. Now this tells us evaluate, so that has a little hint that there is going to be an answer, but there might not be, and that's the comment that we have here on the side, which we will get to momentarily. So the procedure from the definition said split this integral at any point that you so choose. So I chose to split at a equals 0 to facilitate my evaluation. Each of these then is a separate improper integral to calculate. Since they are separate, I write them each as limits, and they are separate limits. They are not to be mixed. And so to make that crystal clear, I choose to use separate variables for the limit to keep things nice and clear, nice and, well, separated. So the first one, right, is from minus infinity to 0. So we've got t going to minus infinity, the integral from t to 0 of our function. The second is from 0 to positive infinity. So I've got u going to positive infinity, the integral from 0 to u of the 1 over 1 plus x squared dx. Antidifferentiate. I mean, it's the same antiderivative. You have the arctan is the antiderivative that you want from 1 over 1 plus x squared. The first is being the limit as t goes to minus infinity from t to 0. The second limit as u goes to infinity to 0 to u. We do FTC2 on both of those. FTC2, keeping the correct top and bottom bounds. So this gives us the limit as t goes to infinity of the arctan of 0 minus the arctan of t, plus the limit as u goes to infinity of the arctan of u minus the arctan of 0. So how to evaluate these? Well, you have to know what is happening in the arctan function. And so the arctan of 0 is just 0, so that takes care of this guy and this guy. as t goes to minus infinity, the arctan of t, well, as t goes to minus infinity, the arctan is approaching its asymptote of minus pi over 2. So I have minus pi over 2. And then lastly over here, the arctan of u as u goes to infinity on the right-hand side. The arctan graph approaches its right-hand asymptote as x goes to infinity, which is pi over 2. So we've got minus, those guys cancel. Pi over 2 plus pi over 2 is pi. So what that is telling us is that this, here is the graph here, y is 1 over 1 plus x squared. It is telling us that the total area on the entire line, so from minus infinity to infinity, the entire area under that graph on all of the real line approaches pi units squared. In fact, we actually say that it is equal to, right? We say that the integral is equal to its limit. So we actually say that that integral is pi units squared. So that was type 1. In the next video, we are going to do a special type of type 1 integral, the p integral, and then after that we will look at what we had above the second type, which was unbounded above and below.